Hello YouTube, welcome to microprocessor tutorial series. In this tutorial we are going to understand timing diagrams in context to instructions of 8085. Timing diagrams are very important from the perspective of understanding the functioning of microprocessor as far as their pins are concerned. What all functions are performed by all the pins at different time intervals is depicted by timing diagrams. Now I presume that you have a thorough understanding of the instructions of 8085 in order to understand timing diagrams. So let us begin. In 8085 we have a lot of pins which perform during the execution of an instruction. I'll write down all the pins which are functional during the execution of the instruction. The first set of pins is the address lines. The next set of pins is the data lines. Then we have read, then we have write, then we have IO/M, then we have the status pins. Now whenever we fetch an instruction from the memory, what is the status of the pins at a given point in time is what timing diagrams is. So timing diagrams will show you the status of all these pins during the instruction execution interval. Now I'll take a few examples. I'll start from a simpler example and then I'll discuss an instruction with 4 machine cycles. Now please understand, depiction of these pins with respect to the clock signal is what we are trying to achieve. So we'll start with example number 1. I'll take a simpler instruction, for example MVI A, 75H. Now let this instruction be placed in the memory location 2000. We know that this instruction is a 2-byte instruction. The opcode for this instruction is 3E and the second byte is of course 75. Now let us assume that this instruction is placed in the memory location 2000 and 2001. This instruction, being a 2-byte instruction, would occupy 2 memory locations, so 3E and 75. Now in order to execute this instruction, let us see the steps involved. Step number 1, microprocessor is going to point to the first memory location address 2000. Step number 2, it will fetch 3E opcode into instruction register. So graphically it is represented as microprocessor going to 2000 and then fetching 3E and putting it in IR. Now bringing 3E from an external location into IR would be opcode fetch machine cycle, and then it will be decoded. Its meaning would be interpreted as an immediate movement into accumulator register of the data which is written next to this opcode in the instruction. So in third step, microprocessor will now point to 2001. Now it will fetch, in fourth step it will fetch 75 as data into accumulator. And that would be classified as an memory read machine cycle. Now opcode fetch machine cycle takes 4 T states. Memory read machine cycles take 3 T states. So when we draw the timing diagrams of this instruction, we should first draw 7 T states and then proceed on to show the status of all these pins in all those 7 T states. So even before we try to attempt to draw the timing diagram, it is of paramount importance to understand the steps which a microprocessor is taking to execute the instruction. Now let's draw the timing diagram. In order to draw the timing diagrams, I'll first draw 7 T states. This one cycle would represent 1 T state, so I'll draw 7 such T states. Now we know that out of these 7 T states, the 4 T states are for opcode fetch machine cycle, and the next 3 T states are for memory read machine cycle as interpreted by the instruction. Now what we do here is we mark up all the pins for which we want to show the status. Now please understand, AD0 to AD7 pins are multiplexed, so they are written as one set of lines. Then A8 to A15 are simple. Then we have address latch enabled. Then we have read, write, status S0 and status S1, and then IO/M. So we'll draw the status of all these pins for the 7 T states. Now, in the first T state, the microprocessor goes to the memory location, which in our case is 2000, and going into 2000 would mean that we would need to write 20 on the higher order address bus, and we would need to write 00 on the lower order address bus. So cumulatively they would make 2000. And in the first T state, we would want this set of lines to act as address lines, so we'll keep ALE as 1. In the first T state, we'll keep ALE as 1. Keeping ALE as 1 would mean that this set of multiplex lines is acting as address lines now. In the second T state, we make the ALE 0 because we want these lines to act as data lines now, and we'll put the data which is written in 2000, which is 3E, onto the data bus, and in the third T state it is brought into the microprocessor. Now, putting 3E onto data bus is represented by read signal, because putting this data onto the data lines, placing this data onto the data lines makes sense only when the read signal is activated, and it is activated by making it as 0. This is an active low signal. So till the third T state, when this data is brought into the microprocessor, the read pin is kept low, and then it can be made high in the fourth T state. Now, in the fourth T state, this 3E is being decoded. This fourth T state is an extra T state which is not present in normal memory read machine cycles, because in this T state it is being read by the instruction decoder. The write signal would not change, it will stay inactive. Inactive would be shown as active high, and the value of S0 and S1 would be would be 1 for opcode fetch machine cycle. Now, signifying a 1 on S0 and a 1 on S1, S0 is equal to 1, S1 is equal to 1, will suggest that this 3E which is being brought into the microprocessor is an opcode. So you should be aware of the values of S0 and S1 for opcode fetch, memory read, memory write, etc. And this data is being fetched from memory, so IO/M would go to 0. A 0 would mean that this is a memory operation. Now, this being said, in the 4 T states, 3E, which is a representative of MVI-A, will be decoded by the microprocessor, and the microprocessor will instruct the address and data lines to fetch the subsequent instruction so that it should be put into accumulator. And to do so, we need to go to 2001, and that can be done by placing 20H on higher order address bus, 01 on low order address bus, making 01 low order address bus as address lines. ALE should be 1. In the second T state, we toggle the status of address and data lines, and we'll make it as data lines, and we'll fetch 75 from 2001. We'll fetch it and we'll place it in the microprocessor in the third T state. To fetch 75H again, read needs to go to 0, write stays 1, it stays inactive, and the value of S0 and S1, S0 will be 0 and S1 will be 1 for memory read machine cycles. So S0 goes to 0, S1 stays 1, and the operation is completed. And again, this stays low because this is being fetched from memory. Now, all the pins in all the T states have different set of values. They are either 1 or 0. What are they carrying? This all is being depicted graphically by the timing diagrams. We have taken up the example of the simplest instruction. In the next tutorial, we'll take up the example of star 2000H. This being a 3-byte instruction and a 4 machine cycle instruction would be interesting to interpret and draw. I hope this introductory session on timing diagrams for 8085 instructions was helpful, and if you found this tutorial helpful, then please click on that like button and consider subscribing to my channel. And thank you for watching this video. You have a good day and a good life ahead. Bye.